My name is Tanwi Mallick. I am an assistant computer scientist at Argonne National Lab. Today I am going to talk about deep learning methods in general, and this will have talk plus hands-on. So before going to the talk, I just want to ask you, how many of you have already used deep learning? Oh, there are many people. And so if you I am assuming that you are using it in your work mostly. And now the question is that how many of you used a device like this in your daily life? Mostly all of you, either Siri or Alexa. So those who have not used deep learning in their work, they also are using deep learning in some way in their real life, right? So do you know how this devices works? So I'm not going in depth of this, but just an overview is that this kind of device actually get the voice, and from that voice they do the speech analysis using natural language processing technique. They analyze from that voice what the user is asking for. For example, here the user is asking for the temperature in Chicago, and that is getting captured by these devices, and they are doing the analysis and understanding what the user is asking for and providing the answers. Here I have a second example. Maybe all of you have used this example, right? So that's is traffic prediction. For example, here I took an example like if you want to go from Argonne National Laboratory to the O'Hare Airport, then probably you search it in your Google Map, and Google Map shows you a path like that. So the maybe I can use the arrow. So this blue line is showing that the traffic is clear here, and the yellow is like little bit congested, and if you find something red, then it's heavily congested. So how does Google do that? So for that, so that's one thing is that they divided that entire roadway into number of segments, and those segments are basically nodes of a graph neural network, and this is the example of graph neural network, and they are connected in that way, and then they are feeding the data like speed, time of the day of the week, to get the estimated arrival time here, like what you see here. So thus actually is known to everyone. So this is a very common application of deep learning. And the third one is that a little bit which we do at Argonne is that NLP for climate research. So all of you know that climate is a very big concern for our generation, because of there are many things like global warming and other things. So all those climate research, what people are doing nowadays is they publish research paper, right? And in those research paper we have those trend, like what is going on, what is going to happen in future, and all those things. What are the biggest concern of today's generation, all those things. But reading those news research paper and getting all those information is very difficult, right? If one human can do that, want to do that, that's going to take huge number of hours, right? So what we do is that instead of going and reading those research paper, doing the categorization, which category this research paper fall into. For example, is it going to talk about, is it talking about some drying trend, or something about extreme snow, or some drought. Instead of that, we do that categorization using weak supervision. So this is another MLTL technique by which you can like categorize the huge number of document in very short amount of time. So here is an example of that. Here those documents are getting into each of this category. Other than that, another thing is that this trend you can find by topic modeling on those documents. So by doing topic modeling, you can find what trend people are talking about in that research paper and the distribution of word in that topic. Along with that, you can also get is the trend over time. So what is the trend which is increasing? What is the concern which is increasing over time, and what can be the adaptation strategies or mitigation strategies for that, what researchers are suggesting. So these are some example by this is just to motivate like why we are talking about deep learning nowadays. So this is maybe a well-known slide to all of you, that deep learning is a subset of artificial intelligence and machine learning, where we can extract pattern directly from the data. So what deep learning is doing, like why deep learning over machine learning sometime we use, and why now? So in machine learning, mostly we provide hand engineer featured. For example, if you want to recognize a face like this, we can provide the edges, we can extract the edges and provide that to the machine to recognize the face. But the thing is that it can be time consuming, and it may not be appropriate for the machine just to by edge, it may not be able to recognize the face very well. So can we learn the underlying feature from the data directly? By using deep learning, we can do that. Is that, for example, here the machine is learning the lower level feature like lines and edges, and these are the mid level features like nose, eyes and ears, and these are the high level feature, that the facial structure. By extracting all those kind of feature by itself, the machine is able to learn how to discriminate one face from another and recognize that face. And why we are doing that now? Because we have this capability of processing or learning that huge neural networks using our hardware like GPUs, which we using that computational capability, we are able to learn those network in reasonable amount of time. And as we are talking about learning directly from data, to do that we need a large amount of data, because the machine because the network is learning directly from data. So we need to provide data. So because from that data is going to learn to discriminate one face from another, for example. So we have a large, nowadays we have large data set, and then this is also supported by our by several software packages like TensorFlow, PyTorch, which are very handy to implement those models, right? So here I am talking about the categories of learning problem, which is the supervised learning, which is the focus of this talk. Along with that, we have like unsupervised learning, semi-supervised learning and reinforcement learning. But as supervised learning is the focus of our talk, I am going to discuss more about that. As the first is, in case of supervised learning, we will be having the label along with the data. Okay. But this can be, the output variable can be continuous. In that case, we call it regression, and it can be a classification problem where the output variable is discrete. So here is one classification problem. You can see that there are the class like dog, cat and tiger, and each of which we have the label like cat, dog and tiger, right? With those labels, we train our network, and after training, we are providing an image like that, and now telling our network what it is, like is it a dog or a cat. So that's a classification problem of supervised learning. So now we are going to know that how can we do that? How can we, how can that network learn to do this kind of classifications? The system which is very good in it is our brain, right? We can do that very easily. We can classify dog, cat, anything very easily, right? How does it work? It has the neurons. The brain is composed of neurons, and these neurons are responsible for learning, and these deep neural networks are inspired by the human brain. And now we are going to learn about the basic cell of our network is called perceptron. So here in this perceptron is a very simple basic unit, right? That's why we are having the input, which are like x1, x2 and xm. All the green are input, and w1, w2, wm are the weight of the network. And y is our output. And here we have an additional term of bias, which is having the weight w0, that is basically shifting it either right or the left, the decision function. And all this are, the weight is getting multiplied by the input and passing through a nonlinear function, which gives us the output y, right? And if you write that mathematically, it is going to be something similar like that, that I is going from 1 to m, and that is basically the all input, and which is getting multiplied by x is the input, and which is getting multiplied by wi over from I equal to 1 to m. And this is the nonlinear activation function, and w0 is the bias. So, so here is one example of the nonlinear activation function. Here is the example of sigmoid. Here you can see the input is going to that sigmoid and activation function, and it is squeezing the input between, and it's between 0 and 1. And that's not the only activation function. We have many more activation function like tanh, ReLU. But the bigger question is like, why we want to use activation function? Because it introduces nonlinearity in the network. So let's take an example. Like here is one example. We have the problem of separating the red dots from the green dots. Okay. So if you want to separate by a linear function, then you can draw a straight line like that, but this is not really separating this green and red point, right? So what we can do is that we can introduce nonlinearity in our network and we can separate the green and red with a boundary of like this. So this nonlinear activation function can approximate arbitrarily complex function. So that's the use of activation function. Now I'm going back to the same perceptron image. So here x is a vector of x1, x2 up to xm, and y is the vector composing all w's. Okay, and this is the way we can write it, that the output y is equal to the activation function, which is taking w0 plus x transpose w. Now if we want to simplify that term, we can write in that way. So here h is this term, and here I drop the weight, but always assume that with each of this line we have the weight associated it, but we are just not writing here just to simplify the network, because I want to make something more complex, multi-layer perceptron, and deep network. So, just for simplicity I am dropping those weights from the network, but we are having the input and bias is also gone, but it's still there. So, if you see the H is basically composing all those terms, but I am not just writing here. So, this is the simplest form of the perceptron, and now if we wanna make a multi-layer perceptron, then that was just single layer out from input to output. Now I am adding one more layer or hidden layer. So, these are the neurons like in this hidden layer. So, how this how we are calculating, for example, H2 is that the same thing W0 plus here it is from I equal to m is considering all input from and xj and wj. So, for this one is getting this input and all this input and getting multiplied with the weight. And if you want to build a deep neural network, that means like the number of hidden layers should be more than one. So, here I added one more layer and the calculation is going to be the same. And let me know if you have any question up to this point, or otherwise I will go to the next slide. So, when we create this network, all these weights are initialized randomly. So, and if we want to predict, like given an image of a dog, if we want to predict what it is, and the network predict it as a cat, because the network weights are initialized randomly. Now, what we want to do is that's a wrong prediction, right? So, we want to penalize our network for that wrong prediction. And how can we do that? We can calculate the loss of the network, which measure the cost for the incorrect prediction, right. So, here is the loss, that is the predicted value and that is the actual value, and the loss is going to take the difference between that two. So, when you combine the loss for all of this input, for example, your input is you have n total input, not this one, but total number of images or something like that. And then if you want to calculate loss for all this thing, all those inputs, then this is going to be something like that. The loss is getting summed over all inputs, and this we called an objective function or cost function, which we want to minimize for our network to make an accurate prediction, right. So, here I am going to introduce two type of loss. One is binary cross entropy loss and another one is mean square error loss. Binary cross entropy loss we usually use for binary classification. So, here is one example. Here we have the dog and cat images and we are passing that to our neural network, and here is the output. So, for example, so the binary classification means like either is true or false. So, whether it is a cat or not, something like that. So, if you see the output here, that's and the output, the predicted output is a probability. So, the probability is telling like how much it is to that how much that probability belongs to that particular class. The thing is that now if a probability of classifying dog is 0.49, then it classified that as a cat, but that's wrong, right. So, if the probability is above 0.5, then the dog will be classified as dog, but if it is 0.49, then it's cat. But the thing is that the probability difference is very little, like 0.1, but we don't want to penalize our network by that cost only. we want to penalize it more because that is a wrong prediction, right? So that's why we use that binary cross entropy. So if you look at this curve, this is a log loss, and if you look at that curve, then if you see the predicted probability when it is going towards 1, the penalty is loss is very low, and when it is doing the wrong prediction is going up, really up. So this loss function penalize more when we are doing a wrong prediction in classification, and this is the equation of doing that. So here like yi will be, so when yi will be 0, that term will be off, and when it is 1, then this term will be off. So more or less that's the concept of binary cross entropy loss. And the second one is like mean square error. So here we are trying to solve a regression problem. For that, so here the problem you can assume, for example, this is we are trying to predict the grade of a student given the hour spent for study and the lecture the student has attended. Okay. So given that two continuous, given that two input to our neural network, we are trying to predict the grade like that. So this is the grade, and this is the actual. So this is the predicted grade, and this is the actual one. Now for mean square error, we are basically taking the square difference between the actual minus predicted and summing up over all training examples. Now the thing is that now we know the loss, and we want to find the set of weights of the neural network. Set of weight means the W's for which the loss is minimum, right? So for that we need to solve an optimization problem. So here is our loss, and we want to find the set of W for which the loss is minimum. So for that you can see like this is W1 and W2 is the solving that problem with two weights, and now we are first randomly initializing the W0 and W1 and starting somewhere from here. After randomly initializing the W, we compute the gradient. So that's basically the loss given the partial derivative of the loss given the W, and the gradient is showing, the gradient is going in upward direction where the loss will increase. So we have to take a step in the opposite direction of the gradient, and that is how we take a step towards, and we want to minimize and go to this point until we converge, like until we go to this point we compute the gradient, take a step towards the gradient, and take a step opposite to the gradient and come to the point where the losses where the for the weight for which the loss is minimum. And this is the algorithm for the gradient descent. So first we initialize the weights randomly using Gaussian distribution and loop until convergence. So what we do, we compute the gradient like this, and then we update the weight. Here it was the previous W, and this is the learning rate eta, and this is the gradient. This learning rate eta is saying like the size of the step you are taking towards. So in the opposite of the gradient to converge. So this is a very important parameter for stabilizing the learning of the neural network. We will discuss it later also. So that is how we are updating the weights of the neural network and repeating it until convergence. So here, so now we are going to now I am going to show you how we are basically calculating the gradient by using chain rule. So for that I simplified the neural network is just one input, one hidden layer, one output, just to understand how can this gradient can be computed. So, here first we are going from this direction to this direction. First we are taking partial derivative with respect to W2, this is our weight, and we are splitting that into two part like JW but by y hat and then y hat by W2. And after getting that one, we can go to the next one, that is W1, and for that we apply the same chain rule, and we are taking H, this hidden layer, into the account here, and this is how we split it. So, we repeat this for every weight in the network using gradient from the previous layer. So, the thing is that so, when we after computing the loss, now we are trying to tweaking this network parameter, network weights, to make it to reduce the loss. Okay. So, for doing that, we are doing this back propagation. Now, after adjusting the weight, we are doing the prediction again, measuring the loss, and after getting the loss, we are doing that back propagation and tweaking the weights again to minimize the loss. That's the way the network learns. Okay. So, I have told you the very basic of neural network, the deep neural network, how can we calculate the gradient, how can we optimize the weight and learn the network to do some prediction. So, but it seems like very straightforward, but in practical the training in the neural network and stabilize the training is not always very easy task, because it has multiple, it's a very complex optimization problem, and getting the convergence is not always very easy. So, there are many things you should take care of while training the network. So, from here I am going for the hands-on session where we will be training one very simple network and see how it is learning, and then we will try to modify that network and see how can we improve the learning. So, for that can you open this notebook? This is in 01 deep learning introduction to MNIST, and if you wanna open it in Polaris like Sam showed you in the morning, you can open it. Other than that, you can also open in Google Colab if you want.
I just have a quick question about your
Yes.
So when you are optimizing your loss function, are you just doing the network loss function, or is it the model function with those like either log or whatever kind of function you want to apply to your tensor network?
So whenever we are optimizing that, we are trying to find the optimal set of weight for which the loss is minimum.
Yeah. So that's in your network, right?
Yeah.
But then do you apply do you take the gradient of the model function where you're applying functions to the tensor network, or like when you're doing the log values?
So in the log, like, are you talking about the cross entropy loss?
Yeah, something like that. Right?
Yeah. So the cross entropy loss is basically telling you how the training is different from that, and then we are trying to tweak the neural network based on that loss. So imagine the neural network is built using the weights. Yes, and now we are getting the loss, like for the given weight what is my loss, and after getting the loss, we are trying to tweak the network weights so that the loss can be minimized. And there is one hands-on example by which you can see exactly what is happening in a very small network, where we are trying to give you an example where everything is handwritten. We are not using the library, so that you can see like what is happening. So, can you open this notebook? Yeah, this one. Yes, everyone. So, first in this example, we are going to build a network which is where we are writing everything by hand, not using any particular libraries or so. So, you can import the packages here. Are you able to do that? And next, we are going to do that on MNIST dataset. So, this is a handwritten digit dataset where you can see an example like all the handwritten digit from 0 to 9 are there. So, you can import this dataset by running this cell, or I can also do it in the Colab. So, downloading the data may take some time. So, let us talk about this data set. So, this MNIST data has the training data, which we are calling XTrain, has the matrix size of it has the images of dimension of 28 cross 28. So, it's very tiny small images. And those images contain 0 to 9, as I have already told you. Now, here we can reshape this and get the training X training and Y training data. So, after reshaping, that's basically like we are taking a single vector, making the 28 cross 28 image into a single vector, so, and the dimension of the vector is 784, and we have this many images of 784 dimension in that data set. Now, if you want to see that what are those images, you can see like in the class level 5, you have the digit written 5 over here. Now, if we want to build a linear model, so here we are defining a linear model. We are taking the W as the W is the weight input and the input images, and then we are doing basically dot product. So, all of you have seen that the input X was getting multiplied by W. So, that is the linear operation we are doing over here. Then we are evaluating the mean square error. So, we are treating that this problem for this time being as a regression problem, and we are calculating mean square error. So, here you can see that was the formula of the mean square error, and we have implemented that. So, that is the NumPy mean of true level minus predicted level square. So, and returning in the evaluation function, and here is the thing we have I have already I was discussing in the slide, is that how we are updating the W. So, W is basically the previous W minus that learning rate time gradient, right. So, here in this learn function we are basically doing that. So, n is the input shape, and here we are getting the predicted level from the linear model, right. So, can you follow that? So here I can highlight also. So here we are getting the predicted level from our linear model with current W and input images, and here we are actually calculating the gradient. So this is basically because of it is mean square error loss. So we are calculating the level minus true level, and then we are taking the dot product, and for and then it's getting multiplied by 2 by n, because if we take the differentiation of this mean square error loss, then it will come like that. And then we are updating the W here. It is our current W, and then it is the learning rate, and this is the gradient update. So if you run this cell, this is just a function, it will run. Now here we define the model, and we define how we are going to learn the model. Now it's time to fit the data, right? So here we are taking the data in batch sizes of 100 and preparing the training X train and Y train like that, and after that here is where we initialize W randomly, and then took a learning rate, initialize the learning rate like this, and kept the number of iteration is 5000, and here is the loss, which is also like 0. And now we started learning. So in each iteration, it is from 0 to total number of iteration. For each iteration we are getting the weight here, and then we are passing that weight. So basically in the learn function we are passing the X train, Y train, our current W and learning rate, and we are getting the updated W, and loss is you can see the loss is here accumulating when we are doing the evaluation. And if you plot the loss, you can see like it's going down like that. And if you want to print the loss in between, for example, if you want to print then you will be able to see how the loss is going down. I am reducing the number of iterations because it will print a lot of values. Oh sorry, I have to just run the previous cells. Oh, I don't know what happened. Maybe I can switch to mine. Yeah. So here like you can see the plot here, and if you just print here, you will be able to see like how the loss value is decreasing. So it's going down, down, down. Up to 500 iterations. And now if you wanna just print those levels, so it's a regression problem, so we are not really classifying here. So that's why the level are all like in between all those digits. So it's not really learning very well, but we can improve that network, right? So here are a few things which we can do to improve the network. Is that earlier it was just x multiplied by w, now we can add a bias term over here. So and we can use the sigmoid function also. So here if you see, this is so the sigmoid function which I have already shown is look like that. And another thing, if you want to do it as a classification problem, you might be doing one hot encoding. So you can provide those class levels and perform one hot encoding. And what is one hot encoding basically? Because so this one hot encoding is basically is saying like class 0 is getting represented as a vector of 10 digit, where the fifth position is 1 because this is class 5 and all others are 0. And similarly class 0, his 0th position is 1 and all others are 0. So we are and for class 4 also his 4th position is 1 and all others are 0. We are basically presenting the classes like that, so that those classes can be treated as independent. It's not like we don't want to train our network like it's a continuous number like from 1 to 2, 2 to 3 like that, but it's all are the discrete levels for that. So for that we are doing that one hot encoding. And then what we can do is that we can introduce we can use nonlinear model like that, where for we are using that sigmoid activation function here, and another function over here, and adding the bias term. So here if you see that we added one more layer in our neural network, and we can add 2 layers also, and then this function will look like this. This is the input and these are the 2 layers and the output. And then this minimizing the loss is a challenging task, because while doing minimizing it can get stuck in the local optima. But there are some trick and tricks which we can do to learn the network well. So first is that like we talked about the learning rate in the gradient descent, right? So here the term eta, and I think Sam also showed this example, like if the learning rate is too high, then it can overshoot, cause the system become unstable, and if the learning rate is too low, then it can get stuck in a local minima and cannot get out of it. So what we can do is that we can do, so first of all we can change the learning rate by trial and error, and we can also adapt some adaptive learning rate. For example, initially it can take larger steps, but when while converging it can take smaller steps, and there are many gradient descent algorithm which help us to make that stable. So here a bunch of algorithm are like SGD, stochastic gradient descent, ADAM, RMSE prop. You can use those and see like how your training is getting stabilized. The another thing is that I really mention here is that suppose you are fitting your neural network, and if if this are the blue are the sample points and you are trying to fit a curve, and this yellow is the true function, now you are trying to fit a model in it. So if it is the linear model like this, so the blue curve then is underfitted, so it's not really representing or fitting your data very well. So if the curve is like that, then it's balanced. If the curve is like that, then it is balanced, and if it is like it's overfitting, if it is like trying to incorporate single point of the data and fitting is very well, then it's not good for generalization. It can do very well on the training data, but for the unknown data set, if is not going to do well because it's too very specific for the training data set. So to avoid overfitting is something which is the commonly used method is dropout. So people usually use regularization to come out of the overfitting issue, and the commonly used method is dropout. What is that? Is that if this is your standard neural network, then you can randomly draw few of this neurons, and this is your network after dropout. So here actually by doing that, you are preventing the network to learn the specific nitty-gritty of the training data. That will help you to come out of overfitting. So these are some commonly used rule people usually do, that is randomly speed the data in 20%, 70% for training, 20% for validation, and 10% for testing, and use the trained data to fit the parameter of the network, use the validation data to compare options, and report the test error at the end of the project. So test data is usually unseen. So with that, so here in this tutorial you mostly explored like without the help of the library what was there in my slide, how can we do the same and train a very simple neural network, right? So next there is another notebook here, that is 2 Keras. You can open that one and see like whatever we have done earlier, what the improvement strategies we discussed, we can do it using our libraries like Keras and improve the network. So are you able to do that? Yes, okay. So we are using the same MNIST data set here, and this time we are not reshaping it. So the shape is same 28 cross 28 because we are going to use a flattener layer. Now here we are building a linear model using Keras, and in that linear model that is basically like x multiplied by w plus bias. So here I have added one layer, that is Keras dense layer, which is composing of 10 neurons, and the activation function is softmax, and then we are basically in the call function we are flattening the input layer, and after the flattening the input layer we are passing that input to this layer 1, which is going to provide us the classes. Now here I am calling the linear classifier, and then linear model which is compiling with the loss of categorical cross entropy. We already discussed about this loss function. You are using SGD, and the matrix we are calculating here is the accuracy. And now it's time to learn. Here is the batch size. So, we are not taking all of the data together, but we are creating mini batches and taking the data in mini batches. We are learning this model for 30 epoch, and let's fit the linear model with the training data. Here we are providing the training data, and that is the level for the training data and the batch size, epochs, and let's start learning. So, here you can see that loss is going down and the accuracy is increasing. So, we are running S for up to 30 epochs. So, after 30 epochs the accuracy increase up to this point, which is yeah, and the loss is like this. Now, if we summarize, if we take the summary of the model, then it's going to show that the network has this many parameters, and for this dense layer, and all these parameters are trainable, nothing is there non-trainable. There's a summary of the model, and if you wanna plot this there's two functions like loss and the accuracy. So, I just train it for 30 epochs. So, it is going down in that way, and the accuracy is increasing in the opposite way, right. So, here we are basically printing that. If you wanna see like where it is classified or where it is misclassified, you can see that example that this 5 is classified as 6, actually that was 5, and this was 4, but this classifies as 6. These are all the misclassification of that network. So, that was a single layer neural network. If you wanna do a multi-layer perceptron and stack more layers, here is one example. Here the first layer we took like dense layer of 20 neurons and added one more layer, which is the softmax layer, like dense layer with 10 neurons with softmax activation, which is going to give you the final output of digit recognition. And here we are stacking it. So, first we are flattening the input in X and passing that to the first layer, and then that output of the first layer is going to the going to our output layer like that. So, we can run that. The same optimization, the same loss function, but optimization is on MSE probe, and we are calculating accuracy. We can, and if you learn the network, so now you see the accuracy improved, like it's 96%, and the loss went down to 2.11. So, that is good. Like now, if you want to try different optimizer, you can change it and try the optimizer, and you can see the effect of adding more neurons on more layer, and if you run. So, here you can see that loss is going down quite nicely than the previous one, and that the accuracy is increasing in a better way. And if you wanna see the previous misclassification, what the network has performed earlier, so yeah, this is the misclassification which the network is still doing. And here you can see a confusion matrix. Like this confusion matrix is basically showing, for example, if for 0th class, how many of the digits are classified as class 0 and how many of them are misclassified into other classes. So if this, so there are two images which was in class 0, that it has the digit 0, but it classifies as 2. There are like, yeah, and one which classified as 3, like this. So you can read that confusion matrix like this, and here are the accuracy in each classes. So good. So here what you learned is that first how to build a simple neural network, linear model, and how can we improve it by our Keras, by adding more layer using Keras software, and improve the accuracy. Now yeah, sure.
Is there a way to know the optimal architecture of the layers, like how many layers do I need to get high accuracy?
Yeah, so that's there is no one answer, because that's a very complex optimization problem, and there is no single solution to it. So what can we do is that we can perform hyperparameter search. So basically we can search for given a range of the hyperparameters for each of these hyperparameters. So for example, we have the learning rate, we have the number of epochs, we have, yeah, there are many more. So we can do a hyperparameter search on those on those search spaces. That's basically going to tell you, that can come up with a network which is like optimal for your dataset, like which can give you best result for your dataset. So that basically, yeah, by fitting those network and taking the loss function and learning that how for this particular set of hyperparameter, what is the loss of your network, and you can like imagine one machine learning model is learning that. So for a given hyperparameter setup, this is the loss of your network. Okay, so one model is learning that mapping. So after learning, it can provide, give you like, what is the set of network which can give you the, so what is the set of hyperparameter for which you can get the get a very good neural network. So are you ready for our third hands-on tutorial? Cool. Let's go to the, oh, you have a question. Sorry.
I was just wondering, the input variables that we're using, they seem to be like a 28 by 28 matrix.
28, yeah.
How is Keras treating that as it gets passed into the neural network? Do you know?
Yes, so yeah, so you will get that intuition better when I'm talking about this network, which is specifically for images. But for the DNNs one, like we are flattening that into a like into a one dimensional vector and providing that. So now I'm going to talk about another network which specifically for images, like, and how that network is going to extract the features from the images. Maybe that was your question, right? Yeah. So we are taking the same data set, the MNIST data set. I have not flattened it, and now I am going to introduce you the convolution neural network, or CNN. So what is convolution neural network? Is that, for example, this is your image, right? This is your image. Okay, so now you want to extract the features from that images and learn your network based on those features. So and this convolution neural network is specifically built for those purposes. What you can do is that this is your filter. Okay, so filter is basically going on this images and performing the convolution operation, and then taking the convolution operation here and repeating it multiple times. So, I have one example what is that convolution operation and how it is giving you those features. So, for example, here you can see that we have the image patch over here, like this is the 3 by 3 patch and this is our kernel, right. So, we are basically doing element wise matrix multiplication between the patch and the kernel, and here we are getting the output over here. So, what we are getting by doing that is that so this convolution filter is basically like getting so is emphasizing or getting the neighborhood information and then convolving into one pixel. So, here basically like if you are having some edges like that, it will get amplified in that single pixel value or something like that. And we are not using one filter here, like there are, so you can see like we learned 32 and 40 64 filters. So, this so all these filters are learning different feature by using the convolution operation, and this is moving over the image and getting the particular feature from the image and learning those features. So, in my slide I have shown you one example of extracting the lower level feature and then higher level feature, mid level feature and higher level feature, that basically you can do using this convolution operation. So, initially you will get the edges and then you will get the mid level features like inos and other thing, and then shape or like high level features like that. And another operation which I am going to introduce is that max pull. So, max pull is the operation by which like you have a 2 by 2 grid and you are taking max of it and making the images. So, what max pull is doing after convolution is that by doing the convolution operation we are like emphasizing the edges or something like that, and then if you see in the images has very redundant structure, like all the nearby pixels are similar, almost similar. So, if you take out the max of it, like you are taking the important feature but reducing the computation because the image size is getting smaller. So, that is how the max pull work. And here we are like defining the network. Here you have like 2 convolution layer, one with 32 filters and one with 64 filters, each of this having like the filter size 3 by 3, and then the activation function is ReLU, and after that we are doing max pulling and then dropout. And dropout I have already introduced you like what is dropout, and that is the dense layer after the convolution layer and doing dropout again, and finally this is our output layer with 10 neurons. So, here in the call function we are basically passing the input in the convolution layer, and then this output of the convolution layer 1 is going to convolution layer 2, and from 2 to 3 pulling from 2 to is going to pulling layer 3, and so on and so forth, and finally we are getting the output which we are returning. So, here is the training of the simple training of the network, where the training network comes. So, we are calling that model over here and then compile that model with the loss categorical cross entropy loss, and here our optimizer is Adam like earlier, and this is the accuracy. So, let's fit the training data here, and why is the training level, the batch size and epochs. If you train the network for 3 layer. Here we define the learning rate, the epoch is 3 and batch size is 512, and if you train the network, then you will see that the losses went down to this number like 0.08 and the accuracy is 97. So here you can plot the loss and accuracy function like earlier. So here you might have a question like in the multi-layer perceptron also the accuracy was like that, and after using CNN it's like 9.7. So what's the advantage of using CNN? The thing is that for this, so it's all of this image data set are not like MNIST. So this is a very basic data set, MNIST one, but you have like lot more complex data set like ImageNet and other thing. So for that, for classifying those images, you need convolution neural network, because by intuition is work on the images like convolve and extract the features. So yeah, so here like similarly you can get the confusion matrix, where you can get the accuracy of each of these classes and the misclassifications also like earlier. And there is one example like there is one example, I'm not going deep into that example because this example is showing like how can you do that learning the iterations by yourself. Like here each epoch you are running each epoch and then providing the batch and then fitting that thing. So instead of using that Keras fit and compile function, you can do it by yourself also. That's one example for that, but mostly is this one, like mostly I have covered everything. So if you have any question, then I'll be happy to answer.